In this video, we'll continue our discussion of simple linear regression by talking about the theoretical model, discussing model parameters, talk a little bit about how we can visualize some difficult concepts such as statistical error, and then discuss interpretation of the different components of the regression model. So first, we're going to start with the theoretical model, and the theoretical model can be written like this, where y equals beta 0 plus beta 1x plus epsilon. Now in this case, our x's and our y's are the same x's and y's we observed before, where the sub I indicates that both of these are from the same case. So remember, each pair of x, y should come from the same individual or the same case. And in this particular model, we're talking about an individual case where that individual's response is given by this beta 0, whatever that is, we'll talk about it in a sec, plus beta 1 times x. Now note quickly that in this model, you can look at beta 0 as the intercept and beta 1 as the slope. This is very similar to models that you may have seen in your high school when you were talking about the equation for a line. That equation oftentimes stated as y equals mx plus b, as y equals mx is this term here, where m is beta 1, that's the slope, and x is just your x variable, plus b, in this case, that's going to be beta 0. Notice that I is from 1 to lowercase n. This is our sample size, or the number of cases in our study. And the error is distributed normally with a mean of 0 and a standard deviation, or variance of sigma squared. Now, the terms in here are called the model parameters, and if you parameters, I can spell, I hope. Now these model parameters, recall that the parameters are from the population. So when we're talking about parameters, we're speaking about the population. This model is for the population in the same way that mu represents the population mean. Now if you recall, we don't always have population parameters, so we use data to estimate these different values. But in the theoretical world, this beta 0 theoretically is the intercept. Now this term isn't used particularly often, but it is useful when we're fitting our model. And if you don't fit a model with an intercept, you do notice a drastic difference. So even though we don't typically interpret the intercept all the time, we do need to make sure that's in our theoretical model. The big one that we care about and most often look at is the slope. So this is the big statistical test that we run with linear regression. It determines first of all, if there's a relationship between x and y, and then further describes that relationship. The epsilon, which is just a Greek e, is the random error term. So recall in our picture where we had a line that we had drawn, and then we had some data points kind of around the line, but they didn't always fall on the line. The distance between the data points in our line is what we would call error, and in our statistical model we write that as this epsilon term. Now with the error, sometimes it's useful to notice how far or how much error there is. The term we use to describe that is sigma squared, which is the error variance, or the variation of the error term. Now if you've taken a mathematical statistics course, you may recognize the expectation. Actually, you may also recognize this from your basic statistics course, depending on who you took it with. The expectation just means the average. So the average of the y values at I is going to be this beta 0 plus beta 1 x sub I. So for every I value, we can, actually we should probably take out the i's here, but for every value we can look at the average or the expected value of the outcome, and that's going to be this equation without the error term. Notice that this is just the equation of a line, so what we're saying is that we expect the outcome to be distributed by this line. Note that if we just had this equation without the error term, this would give us a functional relationship, that is, just a straight line. It's the error term that gives us the statistical relationship and implies that we're modeling more information than just that functional component. This can be difficult to visualize what each of these components mean, so quickly I'm going to go on and copy and paste an image and we'll talk through it together. In this image, we can see a display of all of these different parameters illustrated together. First of all, beta 0, the intercept, is where the line crosses the y-axis. Just your regular old y-intercept. Beta 1 is the slope and indicates the steepness of the line, where beta 1 being positive indicates a positive relationship, just like we had a positive correlation, and beta 1 being negative indicates a negative relationship, just like we had a negative correlation. The epsilon is a much trickier term to understand, but if you think about this line as our expected value, that is, this line is this equation for all of the y's and x's, then you can think that epsilon is something in addition to this line. So we have our line, and for every point on the line, we have some deviation from the line. Recall that in our earlier image, we had a line, we had a whole bunch of dots around it, but the dots didn't all fall exactly on the line. So how do these points deviate? Well, if you recall, epsilon is distributed as a normal variable. That is, it has this bell-shaped curve. So for every point on our expected value line, we have a bell-shaped curve of error. This is where the dots are going to fall into. The higher the bell, that means more dots are going to fall closer to the line, and then further away is the lower the curve, and we're going to have less points fall further away from the line. So this is a great visual illustration of what epsilon is doing. Now sigma squared is seen here in terms of the width of this curve, and I'll note that this curve is the exact same at every point on the line. It doesn't change widths as you go up and down. This is an assumption called constant variance that we'll come back to in a couple chapters. But the curve is the exact same at every point on the line. The same middle, which is 0, and the same width, which is sigma squared. So as sigma squared, or the variance, increases, the width of this curve gets bigger and bigger and bigger. So if we had more error variance, we have a wider curve, and our data are strewn about in a much broader swatch of this graph. If we have a sigma squared that's smaller, this curve becomes even narrower, and we have data that's strewn about in a much narrower portion of this image. So sigma squared is going to be how far our data are strewn from the line. This error term is just indicating that data are not exactly on the line, and the distribution of the data around the line will be roughly normally distributed. Not normally distributed all the way up and down, but normally distributed around each point in the line that the data are at. So now we're going to move on to statistical interpretation. In this class, we'll focus a lot on interpretation, and that's because for many, they can run regression analysis using software, but for many, they also struggle much more interpreting the results. So we're going to focus on the interpretation of the results. Beta 0 is going to be the expected value. And remember, expected value is just the average of the response. That's the y value when x equals 0. Now this is it's a technically correct interpretation, but it's not particularly useful. You'll hear me talk about two types of interpretation, the statistical interpretation and the practical interpretation. This is a very statistical interpretation of an outcome that, whatever this number is that we'll find using some equations we'll talk about later in this video series, that number is just the expected value of the response when x equals 0. Again, technically correct, but very mathy and not particularly meaningful. Similarly, beta 1 represents the expected or average increase or decrease, depending on the sign. If it's positive, it's going to be an increase. If it's negative, it's going to be a decrease. And the response for a single unit increase in x. And again, I know these are yucky definitions. In fact, one of the reasons that we're writing them is to get the yucky definitions out of the way. So these are things that I do expect you to know. I do expect you to be able to talk about. Beta 1 is the average increase in the response for a single unit increase in x. So when x goes up by 1, beta 1 represents how high y goes up. This is the traditional interpretation of a slope, by the way. So if you remember the slope interpretation from your high school class, it's the traditional interpretation of a slope. For practical interpretation, we're going to think a little bit more outside of the box. And note, just like we talked about before, this depends on context. So we can't really have a practical interpretation without the context within which we interpret it. As we move to a practical note on interpretation, though, I want to talk about some possibilities that come up with beta 0. And I can write, hopefully, there we go. So beta 0 has some weird things that happens with it when we move to practical interpretations. Namely, beta 0 sometimes doesn't have a practical interpretation. That is, it doesn't make any sense. And we'll talk about a case where it doesn't make sense, and that's because it doesn't have an interpretation. And we'll talk about a case where maybe it doesn't make sense, but it still does have an interpretation, and we'll hit that in just a bit. Think that if x equals 0 isn't possible, that's a case where we may not be able to interpret beta 0. So let's say that it's not possible. This is the number of attempts. And we're going to talk about an example right now. That's the number of excellent throws that you make in Pokemon Go, and then how old the player is. So if you're 0 years old, you're not going to be able to make any attempts whatsoever. So in this case, interpreting beta 0 when x is 0, that is when your age is 0, interpreting the y value, it doesn't make any sense because your age at 0, you can't make any attempts if you're just being born. So again, sometimes beta 0 isn't going to have a particularly good interpretation. In this case, though, we can do what's called centering the variable. And all that this means, I'll give you the quick equation here, but a centered x is just x minus x bar, or x minus the mean of x. Now if you think about what x minus the mean of x does, x minus the mean of x takes the middle value of x and places it at 0. Think about this. If the x value is the mean, then the mean minus the mean is going to be 0. So pretty much it takes all of your data and just slides it to the left such that the middle data point now becomes 0. This helps to make the intercept more meaningful, as it would then be interpreted as the expected value or average of the response when x is at its average value. And if you think about this, interpreting something, well, what on average is the number of throws or the number of attempts when you're at an average age? That actually does tend to make sense in a lot more contexts, as opposed to saying what's the average number of throws or attempts you would make if you're 0 years old, which doesn't make particularly a lot of sense. Sometimes the centered value is denoted by a little x. You'll see this in some different textbooks. Honestly, I can't remember if they do it in our textbook or not. They do it in some famous regression textbooks. I may or may not include this notation. I'll try not to because it does get kind of confusing, but it is good to know about that sometimes you'll see the little x and that's what it'll mean. All right. So let's talk about a practical interpretation example. So for our example, x is going to be the age of a player and y is going to be the number of excellent throws in Pokemon Go, and let's say out of 10 tries. So we've got a few different Pokemon Go players. We're going to be looking at their ages, and then we're going to ask them to throw 10 Pokeballs and see how many of them are excellent. Note, by the very nature of this design, that this is not an experimental design, so we can just look at association. We can't look at causation. Think about why that is. For it to be an experimental design, we would randomly have to assign people ages, and realistically, we can't look at somebody and say, okay, you're 20 years old, and okay, you're 10 years old. Unfortunately, age doesn't work like that, so we can't study that. What we can study is if there's a relationship between age and the number of excellent throws, not if age causes you to throw better or worse. So our model, we have y equals beta 0 plus beta 1 x plus epsilon. Now sometimes when I write out my model in an applied situation, what I'll do is I'll actually write in the variable names. So in this case, y is throws and x is age, and this makes my equation a lot more readable. My outcome is throws, my independent variable is age, and I'm studying the relationship between the age of the player and the number of excellent throws they can make. In our example, let's say that after data collection, we fit a simple linear model, or a simple linear regression model. And our beta 0, let's say, was 2.9. And our beta 1, let's say, was 0.5. So this is the model we get. In fact, actually, let's just write this out, because there's a couple technical issues that we'll run into if we do it the other way. So beta 0 equals 2.9, and then beta 1 equals 0.5, let's say, for the purposes of our analysis, that this is true. And our goal is to interpret these data points now. That's our goal. So what do these values mean? So let's start with this beta 0 number. Yeah, it doesn't want me to copy it. There we go. Alright, so for beta 0, what does this value mean? So statistically, and we'll break it up into our interpretations. Statistically, this would imply that when an individual's age is at 0, we expect them to make 2.9 excellent throws. And again, we're using expect language here. Another way that you could say this without expectation language is to say that when an individual's age is 0, or when an individual is 0 years old, they would make 2.9 excellent throws on average. So you can use the term expect for expected value, or you can say things like on average. That said, practically, we observe that it is impossible for 0-year-olds to play Pokemon Go. So practically, this doesn't really make much sense, because 0-year-olds isn't really a thing. If we could interpret, we could discuss how we'd expect, on average, infants to make about 3 excellent throws. One thing to note is that when I'm doing the practical interpretations, I'm not going to stick with decimals. I'm going to start rounding things. Think about describing this to your little brother or to a sibling. I don't want to say they make 2.9 throws. I might say, yeah, for infants, they make about 3 excellent throws. Now note that we could look and see if any data is actually close to this, if we actually have any data on infants or 1-year-olds making throws. If we don't have any data around there, we might practically say any conclusions about ages being lower than 3 aren't really supported by our statistical model because we may not have any ages lower than 3 that we're studying. So I don't know how we're going to make any conclusions on that. Or we may not trust that data. We'll talk about that concept later too as we begin to talk about a concept called extrapolation, which is taking your model beyond your data. All right, so let's talk about the slope statistically. This would imply that that the average increase and the number of excellent throws for people older by 1 year. So if you're 1 year older, that's awkward to say. How about for people 1 year older? That's way better. Is 0.5. Okay, well, that's fine as well as it goes. Note that even in my statistical interpretations, I'm including the outcome, average throws. I'm including years old, my independent variable. So the statistical interpretations aren't just yucky because they don't include the context. They actually should include context. Statistical interpretations are yucky because though this is technically true, it's not telling me a whole ton. But let's take out some of the key pieces here. First of all, one of the things that I note is that this is an increase in the number of excellent throws as a person is a little older. So if you get older, you're going to increase in the number of excellent throws. Now, just like with our slope, if you think about if we increase 1 year, we increase by 0.5 excellent throws. If we increase 2 years, we're going to increase by 2 of this, so 1 excellent throw. And I might talk about that, again, trying to use round numbers to describe this. So if someone is 2 years older, we would expect them to make, on average, 1 more excellent throw. One last thing I might think is maybe there are some practical limitations to this, and this is important to talk about when you're doing practical interpretations, is limitations of your interpretation. So thinking through this, remember in our context, we only had 10 tries. So if someone's 20 years older, they can't possibly have 10 more excellent throws because they only had 10 tries total. So we may point out the fact that this is true up to a point, but there is a practical limitation. Can't have more than 10 excellent throws. And these are good things to point out, whether you're doing it for a client who you're doing an analysis for, you're doing it in research where you want people who are reading your research to understand these points, or whether you're doing it for a boss where you want your boss to be able to fully comprehend exactly what you did and not just what it means. Again, many people stop here. This is where textbooks will tend to stop. But what it actually means practically, how people can act on the results that you have presented. So for beta 0, let's real quick talk about some more thoughts on its interpretability. We talked earlier about how sometimes isn't always interpretable, that's okay. Beta 0 doesn't always need to be interpretable. Like if you have a beta 0 value that there is no interpretation for, you didn't break statistics. It's really okay that your model incorporates a beta 0 that's not interpretable. This is relatively rare. Because it depends on if x equals 0 is reasonable. So if x equals 0 is reasonable, then you're good to go. So the only times that you're going to run into interpretability issues is when x equals 0 is not reasonable. So 0 doesn't make sense on your x scale. It's worth noting that sometimes we get unrealistic y values. Even if x equals 0 is reasonable. And these can be interpreted kind of. So you can interpret this. This is something I mentioned earlier in this video, where you can get unrealistic values but still can interpret them. If x equals 0 makes sense in your context, then even if y is unrealistic, you can still mention that interpretation and still talk about what that would mean. And you can talk about how that y value is unrealistic, but what that will end up being is the lowest realistic y value, as opposed to the case where x equals 0 just doesn't make any sense at all, where we shouldn't have any kind of prediction on that value. And I mentioned this idea of centering earlier. Let's talk a little bit more about it. As we mentioned earlier, the centered value of x is the mean of x. So when x centered, the centered variable x is 0, that now represents the mean of, we can maybe write the original x. And this is a really, really, really useful. In fact, we may be able to just write this for beta 0 interpretation if you're interested. And also in later and more complex models we'll talk about this. So for instance, it'll reduce your variance inflation factor, it'll add with interpretability of main effects when we're dealing with models with interactions, etc. So this idea of centering the variable x, and as a reminder, that just means take every x value, subtract the mean, and then use that new variable with all of the x values with the mean subtracted in your analysis, is a useful concept, and it's one we're going to come back to later on. All right, well, in the next video, we're going to talk about some of the features of simple linear regression. In addition to some of the different fitted model parameters, we're going to discuss some of the different ways in which we look at models, and in fact, we'll probably get to how we calculate our estimates of these values. That is, how do we go from a whole bunch of messy data to actually getting an equation of the very, very best possible line that we could use to fit it.